So this is a special topics lecture in the series of classical differential geometry for physics students. And today we want to look at three-dimensional curves. We've seen that curves in 2 dimensions have curvature that tell us how quickly the curve deviates from its tangent. And now in 3 dimensions there's also a torsion, a parameter that tells us how quickly the curve deviates from the plane. So let's introduce those ideas. So we consider a curve in R3. Here's a picture of a curve in R3. Okay, so it's a good old Euclidean R3, parameterized with an x, y, and z Cartesian axis, for example. We'll parameterize the curve with arc length. We found that that's the easiest way to go. We get the simplest formulas that way. We'll get the formulas for other parameterizations by using the chain rule. But in general, the arc length is just the line integral over the curve, adding up the incremental distances as you go. So I can write that as dr, or I can write it as the derivative of r with respect to a parameter times the differential parameter, and that's the way to go. And it's absolute value there. All of the increments are positive. Okay. And so now we want to turn to 3-dimensional curves, and we're going to label a 3-dimensional curve with 3 unit vectors. Okay, the first one, of course, comes to mind is the tangent to the curve. Okay, we'll write that as t of s. It's a unit. It's a unit vector, right? Because it's dr by ds, and for arc length, that's the parameter. The magnitude of this object is, of course, 1. Okay, the curvature of the curve indicates how rapidly t changes. Okay, how rapidly the tangent moves in changing its direction, and we define the curvature as the parameter between the rate of change of the tangent with respect to the arc length and a normal to the tangent, which indicates the direction of its acceleration. Right? T prime, that's r double prime. I refer to that as acceleration. It's a little casual notation, but it's often done, and it brings to mind some good ideas. So here's r of s in red. Okay, here's the tangent at a particular point. It's curving in that direction, and so I'll show. So it's accelerating in this direction. If I choose t and n to be in relation to one another as I is to j, as x is to y, then I draw n in this direction, and with this convention, kappa will be positive, and kappa will be 1 over the radius of the best fitting circle to the curve at that point, as we discussed in the past. N hat, the direction of the acceleration is perpendicular to the tangent itself, and we know that that's the case. That follows from differentiating the normalization condition of the tangent, as we've seen in lots of different applications. Okay. So now for 3D curves, in addition to the tangent, okay, and the direction of the curvature of t prime, t and n, we need another independent vector, and we form that just by taking the cross product of t and n. Okay, it's called the binormal, and there it is. Okay. So it points out of the plane. These two vectors, parameterizing a 2-dimensional plane in which a planar curve would live. Okay, but now perpendicular to it, okay, I can form the cross product and get a unit vector out of the plane, and that's called the binormal, and that'll parameterize the 3-dimensional character of the curve. So T, N, and B is a right-handed orthonormal basis, and anywhere along the curve I can draw it like that, and there you go. T, N, and B, orthonormal basis. Okay, as we move along the curve, this basis will swivel and tilt and what all. Okay, and so we'll want to write down the equation of motion for the triad, and that equation of motion for the triad will tell us how the curve move, and will label the curve in a unique fashion of the boundary conditions. Okay, we need the equation of motion for the triad. Okay, so in other words, I need the derivatives of each one of these members of this orthonormal set with respect to the arc length. The one I don't have yet is the rate of change of the binormal, so let's do that. It's defined as this cross product, and I can differentiate that. Okay, I'll get two terms. The first term with goes like t prime cross n, right? So that's the acceleration crossed into the direction of the acceleration. Well, that's 0, so that term doesn't contribute. But the other term, the tangent cross the rate of change of the normal n hat will, and there's my non-zero term. Okay, so I learned from this that b prime is perpendicular to b. That just follows from the fact that b is normalized, and it's also perpendicular to t. That's what this says. It's a b prime is a cross product of t and n prime, so it's definitely perpendicular to t. Therefore, it lies in the only direction left available, which is n itself. Okay, so it's proportional to n, the direction of the acceleration of the curve, and the proportionality is defined by minus the torsion. That introduces the torsion into the problem, and the minus sign is put there because it's convenient later on. It looks rather arbitrary, and I think different books might use different definitions, but this is the one that's most common, and is the one chosen in the reference for the course, the book by Manfredo Di Como. Okay, so here's the equation of motion for B. I have the equation of motion for T. That's just T prime is equal to kappa n. And finally, I need the equation of motion for n itself. So I want to differentiate n. Well, it's convenient along the way just to remember that T, n, and B form an orthonormal basis, so I can get the third one from the cross product of the other two, and here it is written down appropriately, keeping track of the signs. So B is equal to the cross product of T and N, T is equal to the cross product of N and B, and N is equal to the cross product of B and T. Okay, keep those in mind. We'll need to use them as we go. Okay, so I want to get the equation of motion for the unit vector n that points in the direction of the acceleration. Okay, points in the direction of t prime. Okay, and so n prime, just differentiating, I get two terms. First term going like b prime cross t. Well, b prime is minus tau n, so minus tau n. In the next term, I get differentiating the t prime here in the expression for n, so I'll get a t prime. But then t prime I know is kappa n, so I put that in here. Okay, and then finally I clean up these cross products. N cross t. Okay, here's t cross n, so n cross t is minus b. Okay, here's b cross n. Okay, so that's and I know the t is n cross b. So that's minus t, and I put those in there, and I see finally that n prime is equal to minus kappa t plus torsion b, and that's my last equation of motion that I need for the triad. Okay, so now I can collect everything up. Okay, we have t prime is kappa n, definition of curvature. Okay, we have b prime is equal to minus torsion n, definition of torsion. And then we have the equation of motion for n prime that we just derived, that n prime gets a bit from curvature in the t direction and torsion in the b direction. Okay, so then I can take these and write it as a 3x3 matrix form. That's a better way to collect it, to understand the character of this evolution equation. How does the triad change as I move differentially along the arc, along the curve? Okay, and so I write down the triad here, T, N, and B. And over here, on the right-hand side, it says this linear combination. So I put in a 3x3 matrix, apply it to T, N, and B, and I read off where my non-zero components are. And it looks just like this. Well, it's a famous equation. It's called the Frenet-Serret equations, okay? And it had been studied in differential geometry from long ago. And we see that the 3x3 matrix here is anti-symmetric. Okay, now I'm asking you to check that the anti-symmetry of the metric guarantees that the triad remains orthonormal as you move along C. That's the reason it has that particular symmetry, anti-symmetric character. Anti-symmetric evolution operator will preserve the orthonormality of the triad. Okay, well, let's look at just a couple of examples. First of all, let's remember that arc length is not always a practical parameter. Integrating the length, the distance along a curve, that if that curve is complicated, that integral is hopeless. But we can deal with it on general principles and use it in general arguments, but in practical applications it might not be too good. So we'll use the chain rule to describe the curve in terms of other parameters. Let's say a parameter u. Okay, and then it's just a matter of changing variables and using the chain rule to get rid of differentiations with respect to s in terms of differentiations with respect to u. And so I do those exercises, and then I come away with these results, and these results are, at least in part, derived in your supplementary lecture notes. Okay. So we'll find that the curvature is the ratio of r dot crossed into r double dot divided by r dot quantity squared. Okay, and it's important to get the cross product here that guarantees that we get the geometry and the fact that the curvature points are perpendicular to the normalized tangent appropriately. Okay, so we see that we get kappa because r double dot is different from 0, and r dot has to be different from 0. The dots meaning differentiation with respect to u. I'm putting dots here instead of primes because primes always mean differentiation with respect to the arc length, and now we're doing it differentiation with respect to a different parameter, so I want to keep that clear. Okay, r dot, of course, has to be different from 0 for a legitimate curve. It has to have a tangent vector. Okay, you can certainly write down curves that don't have tangent vectors, that have cusps in them and such, but I'm interested in the regular, a regular curve is differentiable at this point. If there are special points in it, I'll have to make concessions for that. And then I can do the same exercise for torsion, a little bit more work, and I'll find that the torsion involves the r triple dot, okay, dotted into r dot cross r double prime, divided by, normalized by, r dot crossed into r double dot quantity squared. Okay, so I get torsion if there's well, one would say jerk, not acceleration, but the next derivative of the position of the curve. Okay, and that curve is going to, for this to be defined, I see that r double dot and r dot are also going to have to be defined. So there it is. Okay, and I can take an example and just work through an example to get a feeling for it. And the helix, of course, is a nice one. Okay, it moves out of the plane and it swirls along the corkscrew as shown in the picture. Here, I've taken the helix and I've unfolded it. I've unrolled it, so it really would be on the surface of a cylinder. Okay, and I've unrolled it to show that here. So as it goes around the cylinder once with a radius a, it moves to a distance 2 pi a, and when it goes over that distance, it rises by an amount which I'm labeling 2 pi b, like that. So for each one of the turns, it increases its height by 2 pi b. And here it's written down, r of t is equal to Okay, in the XY plane, just ordinary circular motion with a radius a, and in the z direction, just linear dependence upon my parameter. I'm calling it t here because it's like time. Okay, and it's linear in that direction. That's the conventional helix, and that's the parameterization in the x, y, z coordinates. Okay, now it's an easy exercise just to differentiate these fellas with respect to t. You're not differentiating anything worse than a sine, cosine, or linear, so easy work to do. And then just calculate that the curvature is a divided by a squared plus b squared. Okay. Okay, and so to have some curvature, of course, you know, you'll need to have the circular motion in the xy plane. Okay, and so a is upstairs. Okay, and then it's attenuated somewhat if the helix is rising in the b direction, and that's then the equation for the curvature for the three-dimensional curve. It involves both of the parameters here. In particular, the torsion itself is proportional to b, okay, because b, you see, tells you how rapidly it rises out of the xy plane, and then it's normalized by a squared plus b squared again. So there's the torsion and the curvature. Okay, so I think that's all I wanted to do about 3D curves. In general relativity, we'll be interested in plotting moving particles, perhaps orbiting spaceships. Okay, and the orbiting spaceship might, in addition to having a position, might also have an orientation. It might be like a gyroscope. So I'll want to keep track of all of that information, and I'll have to put a triad into the spaceship and see how it evolves in time. So I'll deal with the relativistic generalizations of these equations and discuss precession, and we do that in some of the supplementary lectures on general relativity, and we come back to some of these considerations in a more general framework. Okay, so that's all we have today, and next time we'll do another special topics lecture.